The topic that we discuss in this video is finding the Fourier transform in the y direction of the 2D Laplacian operator. Fourier transform is a really important tool if we need to solve differential equations, and is especially useful if we want to solve partial differential equations. Here my function is a function of two variables, x and y, which are the spatial variables. Is a smooth function. This property is for the function is this function is smooth and belongs to this class C02, which means that is continuous and also continuously differentiable, which means I can take first derivative and second derivative of function without any problem. And here I have some conditions where u with respect of the function, the partial derivative with respect to y is equal to 0 as y grows. And under these assumptions, I want to show that the Fourier transform is S. U is this S is this spectral operator involving the Fourier number xi, which is strictly positive. So this spectral operator, it has the second derivative, partial derivative with respect to x minus xi squared, and here u is the transformed quantity, Fourier transformed quantity. So we have to prove this result. We write the proof. Fourier transform of the Laplacian operator in 2D. We just use the hat symbol, so it's the integral over the real line of the function of the Laplace operator acting on the function u e to the minus I xi y dy, partial Fourier transform in the y direction. Of course, this is second derivative of u with respect to x plus second derivative of u with respect to y e to the minus I xi y dy. We split the integrals here. This can be written as u y y. Now here we need to be a little bit careful. Here we do integration by parts. Is uy times the exponential, complex exponential. So we apply integration by parts here. This here, because I have the differential is dy, the operator can commute with the integral. So I have the partial derivative with respect to x of the integral of u times the exponential. Now I have to do integration by parts once more, plus I xi. This is inside the brackets u times the exponential minus infinity to infinity plus I psi Let me write it because I don't have space. So it's plus xi, and then it's the integral, and I close the parenthesis. So now this bit is the Fourier transform u hat plus. From the assumptions, I know that my partial derivative vanishes when y grows, so this term should go to 0. And also I know that the function vanishes as y grows, so this will also go to 0. And what I end up with is xi squared u hat. So this is just second derivative of u hat, the Fourier transform of partial Fourier transform of u, plus, of course, I squared is minus 1, so it's minus xi squared of u hat. So what I get is the following result. So it's minus xi squared u hat. Now I can write it in the following way, that the Fourier transform of this of the Laplace operator is S operator applied to the Fourier transform u, and S is just the second partial derivative with respect to S minus psi squared. So when I get to the Fourier transform, what I get is the second derivative, special derivative with respect to x, and then I have the component that denotes that Fourier number is involved. This technique helps me to solve the Laplace equation using Fourier transform. Of course, this is for two dimensional Laplacian operator. You can obtain results for more than two coordinates, but we are interested in the two-dimensional problems, solve two-dimensional problems. So here we just study the two-dimensional operator for when we are in the plane.